Hi everyone, I'm Neel, and today I'll be talking about UNCAP, uncertainty-guided neurosymbolic planning using natural language communication for cooperative autonomous vehicles. This is joint work with my collaborators at UT Austin. Despite the advances in connected autonomous vehicles, there are still open challenges in large-scale coordination of CAVs, revolving around efficient communication and interpretable decisions. Existing approaches rely on transmitting high-bandwidth data and do not account for uncertainty in perception and decision-making, which makes them hard to scale and trust. Hence, the key question is, how can CAVs communicate efficiently while accounting for uncertainty to make informed decisions? We present UNCAP, a multi-agent, open-set, neurosymbolic cooperative perception planning framework that is bandwidth efficient and uncertainty aware. OnCap achieves state-of-the-art driving performance, lower bandwidth usage, and reduced uncertainty. Let's take a look at the core methodology of OnCap using this example with three CAVs in green, blue, and purple. In the first stage, BEAR, we enable reduced bandwidth data exchange, that is, only possession and velocity information is shared. In the second stage, that is, SPARE, based on the position and velocity, relevant vehicles are identified for further selective communication. For instance, here only V1 and V2 communicate as information from V3 is irrelevant. Next, using conformal prediction and mutual information, OnCap quantifies the value in shared information. For instance, V2 sees this orange car line of sight, however V1 cannot, and hence V1 can obtain a low uncertainty and high information gain insight from V2. Likewise, the same applies for this brown car for V1. The shared information is then fused and used to construct a structured input message for a VLM for decision making. The key advantage of OnCap is that it is not only bandwidth efficient, but also yields improved driving quality while being zero-shot and generalizable across multiple models. We test OnCap on the OPV2V dataset featuring diverse realistic driving scenarios, and I will first present a few qualitative results. In this highway merging scenario, we have three CAVs equipped with front cameras. Here, non-CAVs are colored in dark blue and CAVs in other colors. CAV 2014 is on the leftmost lane and CAV 2005 is on the rightmost lane, while CAV 1996 is trying to merge. While the ego vehicle is merging, if we have an accommodating driver, without communication, there can be a collision. However, with OnCap, the ego vehicle recognizes yielding behavior as communicated by the helper CAV, enabling confident and collision-free merging. Similarly, an aggressive driver will yield in the ego vehicle proactively stopping and a collision-free merging as depicted on the right. We invite those interested to check out a more diverse set of scenarios and results through our paper, codebase, and project webpage. Moving on to quantitative results, we note that using the selective communication framework leads to a minimum of 63% bandwidth saving, both using text or images. Moreover, OnCap consistently outperforms baselines, yielding in a 31% increase in driving score. More importantly, OnCap yields in a 81% increase in decision confidence and a 30 times increase in information gain compared to non-cooperative planning. Not only is OnCap a zero-shot approach, it also generalizes to various VLMs. In summary, we introduced an uncertainty-guided, neurosymbolic, multi-agent natural language cooperative planning approach that enables efficient communication via text, which achieves state-of-the-art driving performance with reduced bandwidth and uncertainty. While our approach demonstrates potential for scalable and reliable cooperative autonomy, we are extending it to relax exchangeability assumptions using robust conformal prediction. Thank you for watching.